Hello, welcome back to our machine learning course. This is Joaquin van Schoren, and today we'll talk about automatic feature selection, or how to select the best features to build better models. Now, there can be different situations in real world where this comes up. First, it could be that you have a problem where you have a lot of different inputs, a lot of different features, and you have no idea which ones are actually going to be related to the thing that you want to predict. For instance, say that you want to predict some genetic trait, right? Say, for instance, eye color. And you have lots and lots of features. Each of them represents activity of a certain gene in a certain sample person, right? So these are thousands of different either genes, or it could be something like SNPs, SNPs nowadays. And you want to predict something like the eye color, like green or blue, hazel, and so on. And you don't know which of these genes are related to the eye color, right? It could be 100, it could be 1,000, it could be 3, right? You have no idea. And the reason that you want to predict those is that most algorithms don't deal well with thousands of dimensions. We've called this the curse of dimensionality before, right? So every time you add a new feature, you need more data to build an equally good model, exponentially more data. Especially every model that has some kinds of distance calculations like KNN are heavily affected by that. And so say that you want to use a KNN or an SVM or so on, then you do want to reduce your number of features. Even algorithms like random forests, which internally do have a good way to focus on the most interesting features, they can also go astray when you have a lot of them. And that's because something called data separation. So say that you have this tree, and every time you split the tree, you split by half, right? And you can have a lot of points in the beginning. Maybe you have a million data points. If you go down your tree, you split the data more and more and more and more. At some level, maybe you only have maybe 10 points left, right? These are still 10 points in thousands of dimensions, right? And now how can you make a meaningful split between those 10 points and thousands of dimensions, right? It's very, very likely that every pattern that you see in this data will be just random, right? Because you can imagine many different splits in 10,000 dimensions. The more dimensions you have, the more likely this will occur higher up in your tree, right? So if you have a lot of dimensions, then this will easily affect the performance of any tree-based model. So we do want to select here as well. I have to say, this is like less of a problem with random forests, but if you go into very high dimensions, it's still a problem. So we do want a way to select the couple of features which are enough, and then all the rest we throw away, so we can build a simple model based on a few features. A second very common scenario for this is where you have a good model, but your model is just too slow or too big on disk, right? So say you have a model which like a very large random forest ensemble or a boosting ensemble, which works very well, but it's slow to train. So some algorithms are really quadratic or cubic, like SVMs or Gaussian processors. But even if you have like random forest, which is reasonably fast to train, if you have a very large forest, it will still be slow to predict sometimes. Right? So, and that may be okay in some situations, but in other situations, you don't want that. You want to have very, very fast predictions, and you want to build simpler models to do that. It could also be that you just want smaller models, right? So if you want to run your model on a device or on a chip, you can't have too many model parameters in there, right? So you want to simplify the model, and one of the easiest way to simplify a model is to reduce the number of features. This also helps with data collection, right? If you have fewer features, you don't have to collect the data for those features, right? This makes data collection much easier. Say, for instance, you have a bridge, and in this bridge you have lots of sensors, and you want to measure how well how this bridge is affected, how it moves, and so on. Maybe you don't need all of these hundreds of sensors. Maybe you only need 5 of them. Right? So if you can select those, then this makes monitoring and predicting the behavior of this bridge much cheaper. And finally, there's interpretability. A model that has fewer features is much easier to interpret. And that's definitely something that's one of the core reasons why we want to do this. Okay, in this video, we'll look at one example, which is bike sharing. So this is a data set about bikes that are shared in Washington, D.C. And we have a lot of information about every hour. Every hour we collect statistics about how many bikes are rented. And we store all of them, and we collect about 18 features of these bikes. So some of them are about the season, like summer, winter, spring, or fall. So this is actually a categorical feature that was binarized. Then we have the weather, it could be clear, misty, rainy, or heavy rain. We have the year, we have the month, we have the hour. Then we have whether it's a holiday or not, which day of the week it is, whether it's a working day or not. Then we have the temperature, the real temperature. Then the field temperature, how we experience temperature. The humidity in the air, the wind speed. And then for fun, we add 2 random features just to see whether that confuses the selection methods. Okay. Now we can see that some of these features are clearly more correlated than others, like temperature. So this is the count, higher the better, hopefully. And we can see that if temperature goes up, typically also the number of bike rentals goes up. Same with the field temperature. The hour is a very interesting one. So we can see that during the night there's very few rentals. Then we have the morning commute, lots of rentals. Over the day it's more or less equal. And then we have the evening commute, and then it dies down back. But this happens more or less over and over again every day. We have some seasonality over the months. So in the summer days there are more bicycles rented than in the winter. Right? And misty is also interesting. So misty, there have only been 3 misty days in 2011, 2012 in Washington, D.C. So that's also a very interesting feature. Okay, now we want to try different techniques to select the best ones among these. So there are 2 categories. There are supervised techniques and there are unsupervised techniques. The unsupervised techniques don't look at the target feature. They just look at the distribution of the features by themselves. So this is definitely less informed and overall less trustworthy. But let's discuss them quickly. So the first one are variance-based ones. So they basically look at a feature and how much variance there is. So say that this is my feature x. If feature x has only one value, like only value 5, then this feature has no information, right? It's 5, every point has value 5. So yeah, that feature is useless. The model cannot do anything with it, so you might as well remove it. That's a no-brainer. It could be that you have lots of examples of 5 and maybe a few at 4 and maybe 1 at 6. So there's some small variance. And there the question is, okay, is it worth keeping that feature just for those like 3 outliers? Or do those points actually encode something very important that we need to take into account in the future for future predictions? So that's sort of a judgment call that you have to make. So we compute the variance for every feature independently from all the others. And if we do that and we list them from smallest variance to highest variance, you see that misty here has a much lower variance than all the others, right? And again, we can see this here. There are only 3 points among these thousands of points which are 1 and the rest are 0. So obviously this has very low variance. So yeah, you could say that this is a feature that we want to remove. That would mean that maybe your model will be worse at predicting misty points, but if that almost never happens, maybe that's not such a bad thing. Right, so that's a call you need to make depending on the situation. You typically do this by choosing a threshold. Like for instance, you want to say I remove features if the threshold is, for instance, lower than 0.01, like put the threshold here, and so every feature which has a variance lower than that will be removed. Okay, that's variance-based feature selection. Another thing you can do is called covariance-based. So there we look whether 2 or more features are correlated. That means that they move together. So as feature 1 goes up, feature 2 also goes up. Or it could be anti-correlated. When one goes up, the other one goes down. Right? So if we find features which are very correlated, then we may not need both of them. We can maybe remove one of them. Now, the problem with that is, of course, that the small differences that there may still be between two features are actually important. Right? And you don't know that because we're not looking at the target. So let's compute the covariance. So there are different ways to compute the covariance, to compute the correlation between the features. One of the most common one is a Pearson correlation coefficient. That's basically the covariance between two features normalized by the standard deviations of both. And the covariance is computed as by taking each feature, subtracting the mean from it, and then element-wise taking the product of all their values. Right? So if feature 1 goes up, it's higher than the mean, and feature 2 is higher than its mean. That's a good sign for correlation, so that increases the correlation. If one of them is 0, then one does not affect the other so much, so that's 0. If one is higher than the mean, or one is lower than the mean, then they're probably anti-correlates that reduce the covariance. Right? Yeah, so it just measures whether two features move in the same direction or not. Also, by the way, because this lecture will be all about features, we're using a shorthand, so xi means feature I. And this is equal to having our data matrix X and taking the ith column. Okay, let's do this for our data set. And if we do it, we get this matrix. This is the covariance matrix, the correlation matrix, sorry. And here we can see that there are some features which correlate a lot. And for instance, temperature and field temperature, they are very related with each other, obviously. So here we could decide that we want to remove one of them. Also, temperature is correlated with summer. That's no surprise, right? So summer is binary, 0, 1, and if temperature is higher, then it's likely summer. Right? And there's an anti-correlation here with winter. If temperature is high, then winter is always 0, right? And other way around. If temperature is low, then winter is 1. So yeah, we can decide whether we want to keep one of these two. Here, there's also interesting correlation between fall and month, but that's just because the months are encoded like 1 for January, 2 February. So obviously, the months in the fall, that's September, October, November, those have high numbers, right? So in those cases, this is fall as 1. So they just correlated because of the way it's encoded. So maybe don't remove those. Right. Okay, then there is a wide range of different supervised techniques, and we'll explore all of them in detail, and then afterwards we'll also see which ones are most valuable and how we can select the best one. We always show these plots, so in this case we show all our features here. We show the importances that are computed by each of these methods as bars here. So in this case, blue bars are for the f-test and the green ones for the permutation test. We'll get back how these work. This is the importance of the features, scale between 0 and 1. And we always set a threshold that we can change. Now, different methods have different thresholds. I'll come back to that. In this case, we'll just leave it to 0.5, which means we take half of the features. So first of all, we'll talk about univariate techniques. So these are techniques that look at one feature at a time. And one of the most well-known ones is the F-test. This just does a statistical test whether a feature has a statistically significant relationship with a target. Another thing we can do is mutual information. So here we measure whether there's information that one feature provides for predicting the target Y. We'll see in a minute how we compute that. Then we have model-based techniques. So in this case, we build a model and then we ask the model to give us an indication of how important each feature is. Right? We can use random forest for this, we can use linear models, we can even use KNN for this. Then we have rubbing techniques. So these are basically black box techniques that just, we give them a set of features, you compute the accuracy or some other performance metric, and we remove features which cause the least drop in performance. Right? So basically we optimize the set of features so as to minimize the loss in performance. We will see many of those as well. And then we have permutation importance, which is actually a model inspection technique, but you can also use it for selecting the right features. Right? So let's dive into these. So the first set of techniques are univariate, which means they only look at one feature at a time. And most of the well-known techniques here is the F-test. What we basically do is we look at a feature and we see whether there's a statistically significant linear relationship with the target that we want to predict. So yeah, basically we do the F-test, then we look at the F-statistic. If that is high, then that feature is important. If we do that for these features, we see these results. So apparently temperature is significant, field temperature significant, humidity, hour, year, and winter. So we can rank all of these features by the statistics. We'll look in a minute how we compute that. And then based on this, we can now start selecting. So there's different ways of selecting. For instance, we can take the best K. Say that we set K to 5, then we take 1, 2, 3, 4, and 5. Then we keep those 5 features and the rest we throw away. You could also select by percentage. You could, for instance, say that you take the 50% most informative features, or maybe the 10% most informative features. You could also try multiple values and then look at the performance to optimize the number of features that you want to select. Another thing you can do is look at the probability of removing useful features. So you do that by looking at the p-value. So if you have an S statistic, you also get a p-value. So if the F statistic is high, then the p-value will be low. Right? And then basically you put a threshold on the p-value. So only the ones that have p-value lower than that will be selected. Okay, so say that you put the threshold alpha at 0.05, then it means that you remove all the features which have a probability of 95% or higher that they are not important. Now, one problem with these univariate statistics are that they cannot detect correlations. Right? In this case here, temperature and field temperature are both deemed very important and both almost equal importance. Right? So this test has no idea, while it's computing importance for temp, but there's not a feature field temp, which has more or less the same information. It can't do that. It also can't detect interactions between, for instance, these binary features like summer, winter, spring, or fall. It will find all of them interesting because it cannot learn that there's any kind of interaction between them. Right? For instance, if it's summer, it can't be winter, right? But these methods cannot detect something like that. There's different ways of, the statistic can be computed depending on what you want to predict. So for regression, we basically measure whether x correlates either positively or negatively with a target. Right? So we compute the correlation coefficient between feature x and the target y. If that is very positive or very negative, we square that. So that's a good thing. And then this is x over 1 minus x. So this basically something like this, right? So it's a scaling factor. So if 0, 1. So if the correlation is low, if the correlation is low, then ethic will be also low. If the correlation is high, then this kind of ethic gets kind of exponentially higher. Yeah, and then we normalize it by the number of data points. For classification, we do something called ANOVA, or analysis of variance, which you've probably seen before. It's a quite simple technique, and basically what it does, it looks whether feature xi can explain the observed between class variance. So what does it mean? So say that we have a numeric feature xi here, and there are some data points on xi, right? So it has some data points, and some of these data points correspond to class 1, some of them correspond to class 2, some of them correspond to class 3, and then we look at all the points for class 1, we compute the mean and the standard deviation, sorry, the distribution of all these points. And so, well, we compute the mean and we compute the variance of all the points in this subset where class is 1. Right? Variance is just the average square distances with the mean. Right? So if this point here, distance with the mean squared. And we do that for all the different classes. So this is for class 1, class 2, class 3. So for every class we get a mean and we get a variance. And then a good feature is one where the means are very far apart and where the variances are very small. Right? So the ideal situation is one where you have where the three classes in this case are very clearly separated by this feature xi. That's the best case scenario. Worst case scenario is where they all sort of overlap. And well, this feature doesn't really tell you. By looking at the value of this feature, we cannot tell anything about which class it's going to be. So the formula is like this. So we compute the means, look at the variance between the means, and we divide it by the average variance of the between class data. Okay. Right. And so yeah, this tells us basically for every feature how important it is, and then for every feature we get the F statistic. Feature 1, feature 2, feature 3, right? Like we saw in the previous one. And then we can use it to select the most important features. Mutual information is also a univariate technique. It measures how much information the feature X gives us about the target. There's different ways to express this. The one I find most intuitive is entropy, or the amount of really information that that feature X tells us about the target Y. So we've seen entropy before, and we define the mutual information between two features as the entropy of feature X. So how much structure or lack of structure is there in feature X? The same for the target Y. And then we look at the mutual entropy between the joint entropy between the two. Okay? So Hx is high whenever X has many different values. Right? So if this is high, that's good because it means that we have a range of values that we can relate to the target. If X would be always the same value, entropy will be low, but this feature will also likely be useless to us. Okay. Same for the target. We hope that the target values are spread out so that we can more easily learn relationship with it. And the joint entropy between x and I. So this is highest when there's no relationship between the two. Right? When these two are completely random noise, then this will be high joint entropy, and that's bad. Right? So we subtract that from the sum of these two. The obvious opposite of this will be something like this, where there's like a clear relationship. So here, the joint entropy will be low. So you want features which have high entropy by themselves, and where you cannot change this, and where the joint entropy between the two is very low. Yeah. Now, we can't compute the entropy directly, but this can be quite expensive. So we estimate it using k-nearest neighbors. Basically, so say that we have feature x. We take a point. If the points around them are nearby, then that's a low entropy feature, right? So if all the points are like bundled up here, entropy will be low. There's not much entropy in this data, right? If the points are very far away from each other, then the average distance between the points and its neighbors will be large, right? And then that's high entropy. If you look at the joint entropy, it's similar. So if we have random data points, then the joint entropy will be large. So if you look at the points and you look at the k neighbors, or the 3 nearest neighbors, or the 4 nearest neighbors, if they are far apart, then this is high entropy. If we have some structure, and for each point the nearest neighbors are nearby, then that's low entropy. Right? So we want data points which have a high spread of features and have a low mean entropy by the target. Or in simpler terms, if a k nearest neighbor, if all the neighbors in this space xy are close together, then this is an interesting feature to use. Okay. So yeah, we do need to choose the value k. That's an hyperparameter. And you have to say which features are categorical because they need to be handled special. If you look at the results here, then we see that there are a few differences. And one of the most striking ones is that features like hour and month here now have a higher value. So it's mutual information blue. So, and f-test was green. So hour is higher, month is higher. And this is likely because these are features which have kind of complicated relationship, which you cannot easily catch with an F statistic. With mutual information is better at capturing that. Right. So it's typically not always, but it's typically a better technique. It's also a bit more expensive to compute, and you do need sufficient data to have good estimates about this. Okay, now much more frequently used are model-based feature selection techniques. So here, these are techniques where you give all the data to a classifier or a model or regressor, depends on the problem, and you then ask it to predict how the outcome, and then afterwards we ask the model how important the features are in those predictions. And we've already seen this come up in early lectures. So in case of linear models, we can look at the coefficients. So if a feature has a high coefficient, that feature has a big impact on the predictions. So in that case, it's a high important feature. We can also look at trees. So trees can also give us an estimate based on whether we split on those features early in the tree. Right? So if you have to make a decision where to split the feature first, we look at the information gain. So if we have a feature, x1 for instance, which is used first to split the data, then this is obviously an important feature. Right? Say in the second level we choose x2, and third level we choose x1s again. So we look at all the nodes, on top of our tree, and we see how often they occur and how high, and that gives us an estimate of how important that feature is. This importance level is sort of hard to, it's typically a small number. It's not easy to give meaning to that. Basically just the higher the higher the importance, the better. So if we do that for different techniques, we do this here for random forest and for lasso, and we see that both give actually quite different results. Random forest pays a lot of attention to hour because, well, it can learn this complex relationship between the hour and the amount of rentals. So that's good. So random forest correctly predicts this is an important feature. It also thinks that temperature is important, whether it's a working day or not, what the field temperature is, and the year. So apparently, well, the later the year, the more rentals are made. Lasso, on the other hand, gives us quite different predictions. And if you look at performance, you can see it also performs much worse. This can be explained partly if you look at these binary features here. So apparently it pays, well, because lasso can only learn linear relationships between the features, right? And if you have these binary features, it's not so easy to learn anything structurally between them. So in this case, lasso is kind of focusing too much on these binary features and not enough on the other ones. On the other hand, lasso gives zero importance to the random feature, while the random forest pays at least some small importance to the random features. Also, as you will see later, random forests are biased to high cardinality features. So these are either categorical features with many levels or numeric features. Right? So any numeric feature like hour, temperature, field, by just being numeric, will already give them higher importance in the random forest. Because if you have a numeric feature, there's just so many ways you can use the split on. So it's more likely that it's used to make those splits. If you categorical ones and you have between 1 and 100 possible levels, then this again gives you many opportunities for splitting the data. And at least lower in the tree, these can actually be more accidental splits. So yeah, that's why it has a slight bias here. We'll see later how we can solve that. We can also use k-nearest neighbors. So the way that works is by taking a point randomly, and then you look at the nearest neighbors. So in this case, we take the two nearest neighbors. And we look at whether that neighbor is from the other class, we call that a near miss, or from the same class, we call it a near hit. And then we look at the distance between them. If we have a feature where the neighbors are between different classes are far away, this feature is probably better because it divides data from one class to the other class better than the other ones. And we compute a feature weight based on this. So the feature weight, initially the feature weight is 0, and then the next time feature 1 is the previous weight plus or point minus the near miss here. Just copy here. Squared. Okay, because it's going to be both ways. So every time we have a point in the other class and it's far away, this contributes to the weight of the feature. If we have a neighbor that is the same class, then we subtract that. So if we find points and according to those points, according to one feature, it's far away from the points of the other class, then this feature is much more important. It's easier. This feature will tell us more about whether a point is in one class or the other, than this one, for instance. There are a lot of variants of this technique. One of the most well-known ones is ReliefF. And that's just a faster version, so it uses the L1 norm instead of the L2 norm. It has some other improvements as well. And there's RReliefF, that's for regression. Now, if we do model-based selection with this or with this, at some point we are selecting which features we're going to reduce, right? So say at some point we want to remove half of them, right? Then we look at all the features which have very low importance and we just remove them. And this can be tricky, right? So if I remove all these ones here, this actually may not be ideal because then the importance of the other features may change, right? This feature here is important, but it was important in the space of all these features together. If I remove some of these features, even if they play a small role, they can still affect the importance of the other features, right? So it's kind of dangerous to drop a lot of features at the same time. Now, to solve that, what you can do is to basically compute the model, let it predict which are the least important features. You remove one of these least important features, and then you rebuild the model. Right? So you move the as least important features. You can choose the number you move at a time. It can be one, can be more. And after you've removed them, you then recompute the remaining importances using another build of the random forest on the data. You can remove some and you repeat. So this typically gives you better predictions. In this case, it's slightly better than the normal random forest. Yeah, you can see that the predictions, the selected features are more or less the same, but there are some differences as well. Like weekday here was not selected by the random forest, but is selected by the recursive feature elimination technique. And same for winter here. Okay. So this can be rather slow because we have to build multiple models, but it's also one of the most robust techniques out there. Then there's a whole class of techniques called wrappers. And this is basically some kind of black box search. So you have a model, and your model will make certain predictions. You have a certain accuracy based on the features you give it, right? So instead you have your random forest here, you give it a subset of features, and out comes a performance measure like the accuracy. So what you do here is you change the features you give it, you see how that affects the output. If you find a set of features which gives you better performance than another set of features, that's of course a better set of features, right? So that's it. It's completely black box search, basically. It doesn't matter what the feature is, it doesn't matter what performance measure is that you have. It just finds the optimal set of features. Now there are different ways of doing that. Of course, you can use any optimization technique to do this, basically. Most commonly used are greedy search. And here we have, first of all, backward selection. So here we start with, we give all the features to our model. Then we remove one of them at a time. Then we look at which of these removed features reduces the performance the least, and then we remove that feature. Yeah. And then you recompute importances and you repeat. Right? So here we start with a long set of features. Each of them is tested, and the one that has the least impact on performance is removed. And then we repeat, we rebuild on the rest, we remove the one that's least important, and so on. Forward selection works the other way around. So here we start with one single feature. We try every single feature, we give it to our model, we see which one has the highest accuracy, and then we keep. And then so this is fixed now. And then we add a second feature. We try all combinations of these two features. We see which one performs best. Then we keep that best feature, and then we add a third, and so on, until you have some stopping condition, or you have the desired number of features, or performance doesn't increase anymore, or well, doesn't increase anymore. There's also another variation which is called floating, which you can do with both backward and forward. And the idea here is that you add a number of important features, and then you remove the worst of these ones. And the idea here is to break this greedy solution, right? So it could be that this feature here was initially more important, but given the other two, so say I have these three features. So this is initially the most important feature, and then we add two more. And now, given those two features, this one is not so important anymore, so we can remove it again. Right? And so we add features every time we add features, and we remove some again. Right? Yeah, you keep doing that. You can also go the other way around and backwards. You start with all, you remove some, and you add some, remove some, you add some. And you can also use the stochastic search, right? You can start with any set of features, 1, 2, 3, 4, 5, right? And then you do mutations, right? You can remove one, so you end up with 2, 3, 4. Or you can replace one, so 1 becomes 5. Or you can do something else, right? So you can do all kinds of variations on this candidate set, and you keep doing these mutations, hopefully going towards the optimal one. So if of these two mutations, this is the best one, forget about this one, and you try to mutate one better. You evolve it far more. One of the most popular techniques for doing this is simulated annealing. Now, with these techniques, we cannot get a feature importance. We just get which features are selected in the end. If we compare this with the ones written by Rich, that's maybe not the best comparison. But yeah, we see that, well, they're mostly the same. There's some small differences as well. Basically, so this actually works quite well. So in many cases, either forward selection or floating forward selection is actually the best technique to use. It's quite a bit more expensive, right? Because you have to build many models and so on. But it does give you very good results. And the last technique is permutation feature importance. So this is actually not a feature selection technique, it's a model interpretation technique. It basically, it's meant to detect which features have the highest importance in the performance of the model. So say that we have our feature space, and we give that to our model RF, and this has a certain accuracy, right? Now, what you can do to see whether a feature is important is you can just shuffle it or permute it. You just shuffle the values here, so you kind of break any relationship there was with the target Y. Okay. If you permute the data points and your accuracy goes down by a lot, then this is obviously an important feature. If shuffling the values does not affect the accuracy, then this is not an important feature. The way you use this for feature selection is by repeating this a number of times. So you shuffle this 10 times, you'll get 10 accuracies, and then you take the mean of these as a measure of the performance of the feature. Right? So every one of these features will then have an importance. So typically we take the mean. So this will be, so say that we look at working day and we shuffle it 10 times, then, well, sometimes it's more important, sometimes it's less important, and we take the mean of those observed importances as the importance for that feature. And the same for the other ones. You just take the mean of them. Okay. If you look at the results, interestingly, these are typically quite close to what a random forest would tell you. You can see the same features are important, but one difference is that it's not biased so much towards high cardinality features. For instance, temperature and field temperature are deemed much more important by the random forest than they are with the permutation importance test. They're still important, they're just less important, they have less of this bias. Okay, that brings us to the end of our overview of feature selection techniques. In the next video, we'll do a comparison of the different techniques on real data, and we'll discuss how to apply them in practice.